So now I will show you application of the phase diagram to understand the dissolution of the inclusion in the molten slag. So this image shows you the confocal laser microscope image while we are taking the dissolution experiment of the MgO particle in the CaO Al2O3 SiO2 slag. So especially from this M21 to M24 slag, we picked the CaO SiO2 ratio, so basicity of the slag, and we simply change the alumina amount from the M21 to M24. And then we put the MgO particle in this slag system, and we found out the very interesting phenomena. So in the M21 and M22, there was nothing happening around this MgO particle, and the dissolution was very fast. And on the other hand, for the M23 and M24 slag, we found out that during the dissolution of MgO particle, some sort of the wall is started forming around the particle, and then this wall slow down the dissolution rate significantly. So we try to explain this kind of the wall formation by using the phase diagram calculation. So this is the phase diagram we draw to explain this kind of phenomena. So this side here, we pick the CaO SiO2 ratio and CaO 0.525 and SiO2 0.475. And of course, this two is the molar ratio of the CaO and SiO2. We calculate from their weight percent, the CaO SiO2. Okay. So for example, if your CaO weight percent is about 50%, SiO2 is about 50%, we can back calculate that what will be the molar ratio, and then this is the molar ratio we picked from that weight percent ratio. Okay. So because in the phase diagram, the corner in each corner here, we have to put the input as a mole. Okay. So for example, Al2O3, we know that there's 2 moles of aluminum and 3 moles of oxygen. Same thing. We have 0.525 moles of CaO and 0.475 moles of SiO2. That's actually one of the corner by fixing the CaO SiO2 ratio. Okay. And then this is alumina. So it means by changing this direction, we can fix the slag basicity, but we can increase the amount of Al2O3 in this way. Okay. And then we have MgO particle. Okay. So this kind of phase diagram, the settable phase diagram is based on the slag composition with the inclusion MgO particle. Okay. So if you actually plot those 4 slag composition from M21 to M24, is the locating on this position. Okay. And then if you draw the phase diagram, if you look at the position of the M21 and M24 to the MgO, so these two is, if you draw the straight line from here to here, you can see that the straight line can be connected through the liquid phase and liquid plus MgO phase directly. And M22 is same. We can draw it from here to here, straight line. But when you go to the M23 and M24, if you want to draw the straight line here, then you have to pass this area and this area. Okay. And this area is, in fact, liquid plus MgAl2O4 position. Here's the MgAl2O4. And this is MgAl2O4, MgO, and liquid position. Okay, 3-phase region. And when you analyze the composition from the outer side here in the slag to the inner side, the MgO particle, we can see how does the chemistry is changing through actually this position here. And that is actually plotted as a circle point here. So we see from here and going this way, and this actually middle wall, this wall here is have the spinel composition, MgAl2O4. It goes here, here, and then inner side of liquid, in fact, have this co-saturation slag composition of the MgAl2O4 and MgO. So co-saturated actually the slag. So this go here, here, and go back to the inner liquid, and then go to the MgO particle. So this kind of phenomena is very interesting. But if you look at the actual phase diagram, you can actually understand this one very quickly. So MgAl2O4 here and Al2O3, if you draw the straight line, it cannot go directly to the MgO dissolution. You have to form spinel, and then you can make liquid inclusion, liquid composition co-saturated by the MgL2 and MgO, and then it goes to the MgO particle, MgO again. So that makes sense. And M24 is same thing. So we can have this way, this way, this way, this way. Okay. So we found out that this kind of the phase diagram is very very applicable to understand this kind of the wall formation mechanism and also dissolution mechanism of MgO particle in this special slab. And however, if you actually think about this kind of phase diagram in the literature, it is not existing because this is CaU-Si to fix the ratio like this, and with the Al2O3 and MgO. Nobody measured the phase diagram like this. Okay, so this is only possible. This kind of diagram can be only calculated by using the thermodynamic database. So good. Then let's try to calculate this kind of phase diagram by using the fact age. So you go to the phase diagram module, and then you have to enter the three species. So the first one was CaO 0.525, and then SiO2 0.475. Okay, so this is molar ratio. Okay, so you have to fix this molar ratio from your weight fraction ratio of the CaO2. Okay, CaO2 in the slag. Okay, it's constant molar ratio. And then I'm entering Al2O3 and then MgO. Okay, the database we need is FT oxide database. That could be enough. And then say okay. And then now you have to think about, okay, this is in mole. However, what you want to calculate, the scale you want to calculate is in the weight, so in gram. Okay, so you have to know this gram is the, so if when you set the axis component, the species you are entering here is all based on in mole. So for example, Al2O3, we are not actually two weight fraction ratio of aluminum and three weight fraction ratio of oxygen. Yeah? This is 2 moles of Al and 3 moles of oxygen. So everything you are entering in the component for your input should be in mole. But when you do the thermodynamic calculation for your axis, you can choose either in mole or either in weight percent. Okay, so this is component. For the axis, you can choose whatever you like. So I'm using gram for the axis. Okay, and then you do the next. And then you can select all the possible phase, all the solution, all the solid phase. And then you can simply go to the variables. And here I have a triangle diagram I want to calculate. And then the temperature, for example, 1600 degrees Celsius. And then you set A, B, C corner. A top corner in this case is CAMG. Very good. And then B corner, C corner will be MgO in this case, like this. And then B corner should be Al2O3. Okay, and then say okay, and then you can simply do the calculation. Sometimes you actually have this kind of the error message, but then you can simply go here and click the PACT-PS database and say okay. Then most of the time you don't have this kind of the error message. So it say that there's no such component is existing, and I mean in the fact stage when you do the thermodynamic calculation, we don't actually care whether this kind of the species is the real species or not. It doesn't matter. Okay, but sometimes package give you warning message like this, then you can simply go you can simply select the PACT-PS database, then you don't have this kind of problem. Okay, so you see here you have slag and you have MgO plus slag, probably it's monoxide is mainly MgO, and then you have spinel plus slag. Okay, and then here you have three-phase region. Okay, so this is interesting actual calculation. You can actually do the much more complex calculation like this. So you can select all three as this kind of the pseudo component. Okay, that's also possible. And even you can actually draw the phase diagram and one of the corner by using the your stream actually the component. That's also possible. So you can save the actually you can do the some thermodynamic calculation in Eclipse program, and if you have to take that actually output of the slag or something whatever as input for the phase diagram, one of the corner for the phase diagram, you can actually do that too. Okay, so when you do that, you have to make sure that your component is not more than about 5 or 6 actual species in the as one actual component. Okay, that's the only limitation, but the rest of them is okay. So for example, here I click, so for example, and then edit, and you can even take a mixture and stream. You can go stream anything. So for example, I don't know whether I have something. So this is liquid iron 1%, manganese 1%, silicon 1% at 600 degrees Celsius. I don't know what I'm doing here, but you can take it like this. And this could be now one of your axis component. Okay. So this is very special case, but in the most of the case, you can simply just calculate like this, pre-calculation, and then enter this kind of the component by yourself. And also, I mean, when you enter this one, it doesn't have to be this and this ratio together should be 1, okay? So it doesn't have to be like that. So Al2O3, you have 2 and 3. Yeah? So you can just say that 5.25 and then 4.75, for example. That's perfectly okay too. Okay, so if you know this kind of the now axis, if you actually know how this kind of thing is allowed in the factor calculation, you can find much more interesting uh, examples for the paydown calculation. Okay, if you have any question, you can always contact me. Thank you very much.